So question 7. 7 isomers of formula C4H8O2, 7 spectra, proton, 7 carbon spectra, and what one is asked to do is to match all of them up, to identify which isomers the spectra are associated with. Now this is a fairly complex problem, which means there are several ways into it. First thing I'd do though is I'd start off with the fairly definitive ones, and that is we're told that there are 2 acids. Now there are just 2 acids with that formula. Butanoic acid, so that's the acid group with the 3 remaining carbons. Now if we take the acid group out of the formula, we're left with C3H7. And there's only 2 isomeric forms of C3H7. You can have just the straight propyl, or you can have what I like to call the isopropyl. Of course, me and millions of other chemists like to call the isopropyl. Okay, so 2 acids, going to be fairly easy to distinguish them because one acid has got 4 carbon signals, the other one's got 3 carbon signals, and when we look at the hydrogens, you can see that we got 1, 2, 3, 4 hydrogens expected for the butanoic acid, and then 1, 2, 3 types of hydrogens expected for this isobutyric acid. So, and then the other lovely thing with acids is that, as previously mentioned, the proton of an acid group is very, very high shift, very, very far downfield. So let's look at the spectra, the proton spectra, that have a very, very high field proton. And we see that we got spectrum H5 and spectrum H7. And of course, I've already done some of the work for you in putting in 1 hydrogen, 2 hydrogens, 3 hydrogens, which means this signal here must be due to 2 hydrogens because there's 8 overall. And then telling you this big thing here is 6 hydrogens, which means this must be 1 and this must be 1. So assuming, of course, that these are the 2 big signals associated with the acid groups, let's go ahead and determine which is which. Well, there's one acid proton, there's the other acid proton. Now let's see what else we've got. This one here, the spectrum H5, you got 1, 2, 3 remaining peaks after you take out the acid, which must correspond to C1, C2, C3. We got a 3 hydrogen group here that's split into a triplet. Well, that is of course this methyl group getting split into a triplet because it's next to the 2 blue protons. So let's pop that one in. Now the next shift, which we would expect to be the one a bit closer to the acid group, C2, is going to be very, very messy because these protons are split not only by the 3 pink ones, but by the 2 green ones. So at the very least, we would expect to see a hextet there, and we can imagine that's the hextet there. And then finally, we've got a triplet here that is associated with 2 hydrogens, so that must be the green ones. Triplet because the green hydrogens are split by the blue hydrogens, but C4 has no hydrogens on it. So H5, butanoic acid. Now let's look down here for the other isomer. You got 6 pink protons, well there's the 6 hydrogens there, split to a doublet. Looks funky because of all those sort of residual little spinning bits there, but it is a doublet, and it's a doublet because it's split by the blue one. And now this one last little proton down here must be the blue one. We'd expect the blue one to be split into 7 if everything is ideal, because it's next to 1, 2, 3, 4, 5, 6 protons. And you can see 1, 2, 3, 4, 5, 6, 7 if you use some imagination there. So H5 and H7 are the 2 acids.